The objective of this video is to determine the distribution of the sample mean and the normal population and non-normal population. The non-normal population case is when we have a really large sample size and we make use of something called the central limit theorem. So, we know what the distribution of a random variable is. For instance, suppose we say that the lifespan of cats is normally distributed with mean 14 years and standard deviation of 1 year. This is not real data, this is just an example. So if that is the case, then I could simply draw a normal curve and say means 14 and compute probabilities and do all sorts of stuff. But if, on the other hand, if I change the question and or statement and said the average lifespan of a cat or of cats is normally distributed, this is no longer just a distribution, rather this is the sampling distribution of the sample mean. In short, the distribution of any statistic is its sampling distribution. So, how do we interpret the sampling distribution of mean? Notice we know that if we have a sample from a population, and let's say the population is all cats, and I collect the first sample, and that first sample right here perhaps gives me an average. Let's just call it x1 bar. And if I went on to collecting another sample, that is going to give us an average. It is not going to give us the exact same average as the previous one. For instance, if I have it as 16.5, the next one, the next sample need not give us 16.5, rather it could give us 17. The next sample that we get from the population may not give any of the last two values, rather it could give us 15. So the average of the sample now is 15. So if we kept on collecting a different sample, we are going to get different values of the average, and that is what we call as sample variability. So typically, if we continue to collect as many samples as possible, eventually we are going to cover the entire population. What do I mean by that? So here is another sample in green, another sample in purple, another sample in dark purple, I guess, and blue, and forest green. And if we keep on going, we'd end up getting lots of samples, and each of them is going to provide us with a different mean. So as an example, if we have a bunch of samples, let's say sample 1, let's name sample 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And each of them would give us a sample mean. I'm going with the same example, the average lifespan of a cat. So we may have 14.5, 17, 16.5, 20, 19.5, 13, 12.75, 19, 21, and 15. So we have now 10 observations, but each observation is a statistic in that table. And more precisely, that statistic is the mean. So what we have here is not just a distribution, rather the sample distribution. So So if we started with a simple sample and we have a bunch of values, let's say we just have one sample and let's say we observe 15 cats and their lifespan, then we would end up having perhaps 16.2, 17, 18.4, 19.5, 21.2, 20, 18.3, 13, 14.5, 12, 12.35, and the sample size here is 11. So we observed 11 cats. So this is going to have a distribution, but that is simply the distribution of a sample. However, if we collected 10 samples and each of them gave an average, and those average values are 16.5, 17.2, 18.3, 13.5, 19.4, 20.2, 12.7, 13.9, 14.5, and 15.2. So here, this is not a distribution of the sample, rather the distribution of sample means, which is what we call as the sampling distribution of the mean. So, what are the characteristics of the distribution of the sample mean? So, suppose we have a simple random sample of size n, which we draw from a large population with mean and standard deviation. The sampling distribution of x bar, which is the sample mean will have the same mean mu, but the standard deviation is no longer sigma, rather it's sigma over square root of n. So the standard deviation of the sampling distribution of x bar is what we call the standard error of the mean, or simply SE. So you can notice here we denote it as sigma sub x bar, but if it is simply an observation, we would call it sigma sub x, or the distribution of a sample, we'd call it sigma sub x. So if we draw samples from a normal distribution, then same example, the age or lifespan of a cat. And let's say if it has mean mu and standard deviation sigma x, then we can conclude that the sample mean, the average value of 10 cats, would have average lifespan, or previous problem I meant to say lifespan. So I didn't mean to say age, I called it lifespan. So the average lifespan cats will have the same mean, but its standard deviation is no longer simply the standard deviation. We call it the standard error, and it is given by sigma x divided by square root of n. So we could also denote it as the standard deviation of x bar. So what changes? The mean doesn't change. You have mu here for one sample and mu there for the average, but the standard deviation is sigma sub x, and that becomes the standard error, which is sigma sub x divided by square root of n. So here is an example. So the weights of pennies minted after 1982 are approximately normally distributed, with mean 2.46 grams and a standard deviation of 0.02 grams. What is the probability that in a simple random sample of 10 pennies minted after 1982, we obtain a sample mean of at least 2.465 grams? So the key word here, or the phrase here, is sample mean of at least 2.465 grams. So what we're trying to find is the probability that the sample mean is greater than or equal to 2.465. Now, what do we know? We know the weights of pennies minted after 1982 are approximately normally distributed, with mean 2.46 and standard deviation 0.02 grams. So the mean, mu, is 2.46 and the standard deviation is 0.02. But we're not asking for the probability of a single penny having a weight of 2.465 grams or more. Rather, we are asking for the probability that the mean is greater than or equal to 2.465. So what we've got to realize is that the mean still has a normal distribution, and its mean will be the same as the original sample, but its standard deviation is no longer 0.02. Rather, it is 0.02 divided by the square root of 10. The reason being we are looking at the average of 10 pennies. So how do we find the probability? We know now that the mean is 2.46 and the standard deviation, got to turn on this calculator. Hopefully it is on. It is now. So we know that the mean is 2.46 and the standard deviation is the standard error, which is 0.02 divided by square root of 10. Let us find the standard error first. It is 0.02 divided by square root of 10, which gives us 0.0063 grams. This is for the average of the 10 pennies, not a single penny. So, as you can see, the original standard deviation was 0.02, but this value, the standard error, is 0.0063. Now we can find probabilities the usual way, second part. Number 2, we're trying to find the probability that the average is at least 2.465. So 2.465 is over there, and we want to find the area above it. So the lower value would be 2.465. The upper value is E99. The mean is 2.46, mind you, but the standard deviation is the standard error because we are looking at the average of 10 pennies, and we found that standard error to be 0.0063, and that probability is 0.2137. So there is a 21.37% chance the average of those 10 pennies would weigh at least 2.465. The average weight of those 10 pennies would weigh at least 2.465 grams. So, in contrast to the previous problem, what I have here is I've changed the question and I simply have what is the probability that a randomly selected penny, typo there, this randomly selected penny minted after 1982 is at least 2.465 grams. Here we are finding the probability x is greater than or equal to 2.465, and we know that we have a normal distribution. The mean is 2.46 and the standard deviation here is simply 0.02, because if we take 1 penny and if we look at its weight, it is normally distributed with mean 2.46 and standard deviation 0.02. So 2.465 is over there, and we are trying to find the area above it. Second mass, we start at 2.465, we end at E99, the mean is 2.46, and the standard deviation is 0.02. And the probability here is 0.40129. In contrast to the previous answer that we had, which is 0.2137, I want you to notice the difference between the previous probability and this one. So if we have to interpret the previous probability, we would say the probability that the average weight of 10 pennies minted after 1982, weighing at least 2.465 is 0.2137 or 21.37%. However, if we have to interpret the probability here, the probability that a randomly selected penny minted after 1982, weighing at least 2.465 grams is 0.4013 or 40.13%. So the same scenario here, but what we have to find now is that looks like it's the same problem, so we can change it to at most 2.8 grams. So we want to find the probability that the average of or average weight of 10 pennies is at most 2.8 grams. So we could draw a bell curve again. The mean here is the same as an individual random variable, and the value is 2.46. The standard deviation, however, is the standard error, and that is 0.02 divided by square root of 10. And we found that value earlier to be 0.0063 right there. So we could use second vars, option number 2, the lower is at 2.8 and the upper is at infinity. So we have 2.8. Oh, sorry, we are doing at most. Let's do this again. So the mean is 2.46 and we want to find the probability that the average of the average weight of 10 pennies is at most 2.8. So second vars, negative E99, comma 2.8, comma the mean is 2.46. The standard deviation is 0.0063. and that probability is 1. What does it say? It is absolutely certain that the average weight of 10 pennies is at most 2.8 grams. So the central limit theorem is an important theorem in statistics, and it applies when we have a non-normal population. In the sense, X could have any distribution. For example, it could have a distribution of that sort, in other words, right skewed, or it could have a distribution of that sort, left skewed. It doesn't matter. What it says is that if we have a large samples, provided we have a large sample, in the sense n is large, which is why we say n increases, then the average will have a bell-shaped distribution, and and its mean would be simply the mean of the original distribution, and the standard deviation will simply be standard deviation divided by square root of n, and that is the standard error like we saw it earlier. So here is another example. Suppose that the mean for an oil change at a 10-minute oil change joint is 11.4 minutes with a standard deviation of 3.2 minutes. Note the phrase normal distribution is missing in action, but the sample size is 35. Typically, this doesn't hold true in practice oftentimes, but if n is greater than or equal to 30, the central limit theorem, CLT, states that x bar will have a normal distribution with mean same as the original mean that is given in the problem, which is 11.42 minutes or 4 minutes, and the standard deviation, which we call the standard error, of mean sigma x bar, is the value of sigma, the standard deviation 3.2, divided by the square root of n, which is 35. So 3.2 divided by square root of 35, and we end up getting 0.5408. So even though the phrase normal distribution is missing in this problem, in the sense we are looking at a non-normal population, we have a sample size that is 35, and 35 is greater than 30. So what does central limit theorem state? It states that x bar will have a normal distribution with mean 11.4, and the standard deviation, which is the standard error of the mean, would be 3.2 divided by the square root of 35, which is 0.5408. And that is the sampling distribution of the sample mean, whatever answer that we wrote. So here is an example. If a random sample of n equals 35 is selected, what is the probability that the oil change time is less than 11 minutes? So this is a tricky problem because the distribution of oil changes is not specified in the problem. Now, if it was specified and if we had a normal distribution, we can make use of normal CDF and find the probability. But that is not the case here because the distribution of oil changes is unknown. We said nothing about the distribution of oil changes. So we are trying to find the probability x less than 11, but we do not know the distribution of x. Which simply means that probability is also unknown. We do not know the answer because we have no information about the distribution of x. However, when we change the question a bit and when we say we have n equals 35 oil changes and we want to find the probability that the mean oil change time is less than 11 minutes. Here we're trying to find probability that x bar is less than 11. So the distribution according to CLC since n is bigger than 30, x bar has a normal distribution with mean. The mean doesn't change, and that mean here is 11.4 minutes. And a standard deviation, which in this case is the standard error of mean. And that value is what we found over here, which is the standard deviation divided by the square root of the sample size. We got 0.5408. So what we have is 0.5408, which would imply that we have a bell curve for x bar because n is greater than 30, and according to CLT, the mean would have a normal distribution. So now the mean happens to be 11.4 for the sample mean also. The standard error, on the other hand, is 0.5408, which is the standard deviation of the sample mean. So we are trying to find the probability that the average of the 35 oil changes is less than 11. So 11 is over there, and we try to find the probability. So we are trying to find the area below 11, and that is given by normal CDF. We start at negative infinity, which is negative E99 in the calculator, and that would be the lower endpoint. The upper endpoint is 11, so normal CDF, negative E99, comma 11, the mean is 11.4, and the standard deviation is 0.5408. And that answer is 0.2297. So the probability that the average time of 35 oil changes is less than 11 minutes is equal to 0.2297 or 22.97%.